Chapter 12, Deflection of Beams and Shafts, Part B, Moment Area Theorem, example number 5. So in this example, we want to solve a two simple support beam with a uniformly distributed load of W. This time with moment and moment area method. We have already solved this problem in a elastic curve derivation from moment and equation, and as well as a load distribution, I think. So I will provide you with the link of them. But this time we want to solve the two-end simple support beam with a uniform distributed load of W. We want to know what delta maximum is and what are the theta at A, and what is theta at B. So let's see how we can approach this problem. So if we calculate the reactions, it just goes by half of the load by each of them due to symmetry. And if you draw the shear, it just comes up by WL over 2, the amount of RA at A, and it just the effect of distributed load, it just pushes it all the way down, and it just comes back by a W over 2 is 0 by reaction at B. If you, and that's a linear shear. So that's a first degree linear. Definitely that goes by a second degree in moment. So in moment distribution method, delta max is simply equal to what? A T A with respect to C, and that's M over EI from A to C times the X bar. Let's see uh, what is that. So if you draw a deflected beam, and that's a over here, that's T A with respect to C, and that is exactly the same value of delta maximum at the center due to symmetry. So if you look at these two heights, they are identical to each other, and this one is just a tangential deviation. That's a tangential deviation of A from a tangent drawn at C. So that's T of A with respect to C. So an X bar is just a centroid to the A, mhm, the point A. So if you want to calculate the moment over area, if you remember, if you have a parabolic spandrel with a second degree, the area of this spandrel is 1/3 of B times H. So that means the rest of the area goes by an area of what? The rest is 2/3 of B times H. And our H is, our B is L over 2 due to symmetry, and our H is the numeric value of our moment, maximum moment is just the area under shear. So M maximum is just area of under shear, which you can easily see that's the area of this triangle. And that's a half of WL over 2 times length of L over 2. That's WL squared over 8 EI. And that's M over EI graph. So far we do know that our T of A with respect to C, tangential derivation of A from C, is just a 2/3 of WL squared over 8 EI times L over 2 mhm, times x bar from A. So if we want to calculate x bar, that's a concept of centroid calculation. Let's do that part and come back to our business. So if you have this second degree parabolic spandrel, mhm, and we already know the centroid for that is a area goes by 1 over 1 plus 1. Area is 1 over n plus 1, b times h, or L times h, if this is L, length of L, and height of h. And then centroid goes by 1 over n plus 2 L times h. So if that's a second degree, a simply centroid is 1 over 2 plus 2 of L, and that's a 1/4 of L from our origin, which is this is the positive direction. And at the same time, if we want to know what is the centroid of our area, which is the bigger chunk of the area for this one, if you remember, we just know that x bar is equal to, if you have different shapes, so you can easily know the area of this area, bigger chunk of area, that's 2/3 of BH. We just solved that in previous slide. And at the same time, that's a area of BH whole rectangle minus a 1/3 of BH. So that's a 2/3 of BH. Uh-huh. And if you want to calculate the centroid based on for only this part, it just simply says if you subtract the whole area minus the smaller chunk of area, it just gives you, so instead of summation of Iyxi over Ai, you just can develop that the area of rectangle times the centroid minus area of the a 1/3 of BH or LH times the centroid of that part, which is a quarter of L. That's a quarter of L. So that's HL, the whole rectangle, a times a half of L. So that's a centroid of what? Centroid of the rectangle from the base, that's L over 2, minus the area of this portion times the centroid of that portion, that's L over 4, over H over the subtraction of the area, which is 2/3 of BH. So that's a 2/3 of BH, we already have it. So HL minus a 1/3 of HL, so that's 2/3 of HL. And if you simplify X bar, it just gives you 5 over 12 over 2 over 3 times L, because it just remains by 1 L. The rest are cancels out. And X bar is 5 over 8 times L for a centroid of the bigger chunk of area, which is 2/3 of BH, and that's from A. So I just need this part. If we go back to our problem, which just says delta max is T of a tangential deviation of A with respect to C, which is M over EI between those points, and C is just center, so that's a point C. This is point C. This is point C. That's M over EI for that part times the centroid to A. So because the measurement is based on A due to second moment area theorem. So, and we already know X bar is 5/8 of or your length, which our length here is L over 2. So that's 5 over 8 times L over 2. So that says our a centroid distance from A is 5 over 8 times the length, which is our length is L over 2. So we already know what is our length, what is our M over EI. So if you remember, our uh, area is 2/3 of a, a L, which is L over 2, this distance, and WL squared over 8 EI, which is H. That's 2/3 of BH. the area of this part times the distance, which is this part. So that's x bar, and that's a 5 over 8 times 2L. And if you do the math, it gives you a delta max, which is equal to a delta max, which is equal to 5WL4 to 384, which we have already solved with a integration method, and you can see how a moment area method is far simpler just due to geometry of calculation. So in that case, if one wants to know what theta A is, they are identical to each other, and because of the due to symmetry of the structure, so theta A is equal to theta B, and each of them goes by a delta max is, as you can see, that's a 5WL to the fourth, that's delta max over 384 EI, and theta A is equal to theta b, and if you just calculate the area under the moment diagram, that gives you W L cubed to our 45 EI. And how that goes, that's something like if you just simply calculate this area. So that gives you what? That's a 2/3 of L squared over 8 EI times L over 2. This 2 is cancelled out with this one, and that's WL cubed over 24 EI. So theta is the first moment area theorem, and the delta is the second one. You can see how easily you can get these two numeric value of delta and theta, which is 5WL to the fourth over 384 EI, and theta A is equal to theta B due to symmetry, and that's WL cubed over 24 EI. We'll solve more a problem in next videos. Thank you.